We will wait for a couple of more minutes before we start with the session. Good afternoon, everyone. Am I audible? Can someone unmute and say if am I audible? Okay, thank you. Yeah. So my name is Siva Poornan. Just a minute. Yeah. Sorry for that. So my name is Siva Poornan. I am a PhD student at the Civil Engineering Department of IIT Madras. And here we'll be having a live interactive session on matrix methods of structure analysis, the NPTEL course. So this will be mostly interactive, as the name itself is interactive. So I expect that most of you would unmute and talk, or we'll have polls and other sessions where you can uh, record your opinions for the questions, or you can help others find their answers, right? So it will be mostly interactive, and that's a basic reason for this session. And here we every week we'll be having at the same slot, Sunday 3 to 4 mostly. If in very rare occasions maybe we'll shift it if there are some unavoidable situations. So here you can ask your questions and we can discuss on how we understand about the concepts and so on. And I expect that all of you would have already taken the basic course of structure analysis, which is a prerequisite, so that we can continue with this course here, right? Okay, so I think it's a very odd time. That's why most of them have not joined. Only I can see only barely 5 people of you, right? That's fine. Anyway, what will happen is even if you miss this live session, there will be a recorded video which will be available in the folder in the NPTEL portal. You will see a link. When you access that, you will be able to see. I think YouTube link would be available. You can see it in the YouTube. The only thing but you would miss is an live interaction. If you want to ask a question, then you have to attend the next week and then post your question, or you can put it in the there is a portal, right? Discussion forum. You can put it there so that we can discuss the questions here during the live session. Okay, so we'll get started. Uh, so before we get into the matrix methods, we'll just recap on the basic structure analysis that you might have studied in the earlier course, so that we know what we are talking about, right? Okay, so can someone say what a structure is? Since we are studying about analysis of structures, which is nothing but structure analysis. So can someone say what we mean by a structure? Can someone unmute and say, or you can put it as a message. What do you think a structure is? Structure is not just restricted towards the civil engineering concept, a mean of transferring loads to ground. Yeah, so that is right, and that is right, that is more specific in the sense of civil engineering or structural engineering, right? But structure is no is an English word, so it has a very broader meaning, right? So for example, we have data structures in computer science. Yeah, form. Yeah, form can be a good approximation of what a structure is. So what I understand by structure is it's a form, as you said, that gets an input from the outer, whatever is outer to it, from the outside to the structure, it gets an input, and based on that input it delivers an output, right? Even in data structures you would have a, let's say a small package of code where which will perform a certain task, right? We need to input certain things and then we get something output from it. So that's what we mean by structure, and structure here also does the same job. Structure, what it does is, as someone said, it takes the load and then it transfer it to the certain some other position, right? It transfer to the ground, or depending upon where it is. You can even have for example, even planes are structures, so they do not transfer the load to the ground, but they transfer it to the surrounding air, right? Okay, and uh, you can even have ships which transfer the loads to the water, so you can transfer it to anything you want. So these, everything comes under the broad classification of structure, right? And the response is in the form of what is the displacement, deflection, and internally we analyze it for strains and stresses, so that we know it is safe enough for the given loads, right? So that's a broad understanding of what we are going to do in structure analysis. We are going to analyze that whatever we are talking about, form or whatever is intended to be built so that it can transfer the load, that we are going to analyze and see whether it is going to stay, is it going to remain safe, and what are the internal responses, how much is it going to deflect, and so on. We need to analyze it, understand it. Okay, now the two main concepts that we talk about structure is strength and stability, right? Most of you would have heard about it. Can someone say what is the difference between them first? A definition of what strength is and what stability is, and then we'll go to the differences between them. What do we mean by strength of a structure, and what do we mean by a stable? What do we mean by stability of a structure? Strength is resistance to failure. Good, but that itself is. Can you please repeat that? Resistance to deflection, is it to not stiffness? So when we, yes. So when we talk about deflection and how much it deflects, it goes to the topic of stiffness, right? And strength, as someone said, can be related to failure. But before that, we need to understand what failure is then, right? What is failure? Because why I am saying this is, when we go to stability also, we can have a failure. Is it not? I don't know if you would have seen, yeah, even in your basic structure analysis, you would have seen systems that can fail due to stability. For example, let's say I have a ground like this, and then there is a ball. This is a very typical example. Let's say I am placing a ball over it, right? And then if there is a small disturbance to it, what will happen? It will roll over, and it will. We can say that this is leading to failure. Is it not? But this does not mean that this ball is not strong enough, right? This talks nothing about the strength of the ball or the ground. It is just that the configuration is in such a way that it leads to failure. So this comes under stability. But you can also have strength issues. So when we talk about strength, the failure is material failure. The material itself, the structure itself has faces a material failure, right? The strain exceeds a particular value that the material fails. Okay, so failure can be classified into two things. One is material failure, wherein we talk about strength, and one is just the configuration, how it is arranged, so that it can lead to a stability failure. Okay, so these two both are important aspects, right? Okay, maybe we can have some structural examples so that you get into context. For example, I'm sure you would know this, but just to get into the uh, common page, we'll do this. So let's say we have a 4-bar truss, right? This is a very common example to study again stability. Let's say we have the supports to be this, or even we can have a roller, right? So this structure, is it stable? Would this, what is it? You will experience a rotation, but experiencing a rotation is not bad, and that does not say anything about stability. For example, if you have a beam and if you have a moment, that will also experience a rotation, right? Let's say I have a simply supported beam subjected to a moment. Won't that be a rotation at both ends? So why is rotation a bad thing? Here there's something. What is it? Because yes, collapse. Yeah, and that more appropriate word is that it is unstable. Collapse me. Yes, collapse is okay, but collapse does not say anything about whether the failure is due to strength or stability. Right? You can have a column subjected to an axial load, and then after a certain load, when the material, yes, material strain is exceeded or strength is exceeded, still it will, here also we say it collapses. Right, so to differentiate between this collapse and this collapse, and collapse and failure are very synonymous terms, we say that, but it doesn't give any it doesn't classify whether it's strength or stability. So it is better to specify what kind of collapse or what kind of failure it is, right? So we can say that it is a stability issue, right? So it's unstable. As someone said, it can have different configuration, right? So when we do the geometry, we will have, understand that because of its spin joints, it can form different configurations without any resistance. So therefore, all these configurations are equally possible. So with any perturbation, it can take any of these configurations, and therefore we say that it is not a very stable structure. So stability is to maintain a position for for small perturbations. Is what is the definition of stability. I hope these are the things that we already know. Just to recollect. Okay. Um, then we'll talk about we in civil engineering aspects, we are focused more on stable structures. We do not deal too much on unstable structures. By the way, I need to point out here that unstable structures are not bad. We think that they are bad because for civil engineering applications, we need to transfer loads and we don't want too much of deflection, and that's why we avoid them. But if you go to mechanical engineering, for example, even the fan that is over you, it's an unstable structure, right? It has a mechanism. It can keep taking different configurations with load, right? And that is what is the use of it. And if it doesn't do so, then there is no purpose of having a fan, right? So unstable structures are also useful in certain aspects, but we don't deal with them. So we call them as mechanisms, and we deal it separately in mechanical engineering. Mostly our structures are all stable. Okay. Having said this, we'll talk about determinacy. I'm sure you would know this also, but can someone summarize what is it? What is determinacy? And by determinacy, we mean static determinacy. Okay, we'll start with that and then move on to kinematic determinacy. What is static determinacy of a structure? Good. That is a good definition. Can you also specify what you mean by number of unknowns? Because number of unknowns is a bit confusing, right? What do we mean by those unknowns? Yes. 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 But as support reactions are only unknowns here? Good. So by unknowns we mean the internal forces. So yeah, member forces is what we mean. Internal forces. Those forces can be in terms of, not internal loads are the right words, because we also have internal moments, right? So what we call as a bending moment. At this point, I would like to slightly deviate and talk about what is a bending moment and what is a moment before we proceed further on static determinacy. Can someone say what is the difference between a moment and a bending moment? Yes, force into lever arm is what we say. Okay, then what is bending moment? Yeah, okay, so but yeah, definition is difficult to understand if we don't understand the physical significance, right? Can you summarize the physical significance before we see about the definition? What is a physical significance of having a moment, and why do we study bending moment? Why do we study moments? Okay, so that is a classification of bending moment. Yes, so that comes later. So we need to first understand what they are before we can understand what are the different types of. Can you please be louder? I think I'm not able to hear you. Yeah, yeah, now it's better. Okay, so I think what you're saying is bending moment is the internal forces created due to external loads. Okay, okay. Yeah, that is a very good definition. And what about moments? Okay. Yeah, so basically, we can have loads in two categories. External loads. When I say load, it's the external loads that are applied to the structure. We saw what a structure is, right? Anything that is coming away from it, outside of it, is what is the external load, right? And that external load can be in terms of forces or moments, right? And those are the loads. So we can have, let's say this is the structure that we are talking about. It can be anything. It can contain a frame, it can contain a truss, it can contain anything inside this box, inside this space. Okay, and then whatever is applied to it can be in terms of forces or moments. So this is what we mean by total external moment, right? So there are F1, M1 and F2 and so on. So I need to satisfy some things. I need to apply the loads in certain way so that this space would be in equilibrium, is it not? So let's say this is a rock, and if I just apply one force, what will happen? It will accelerate. It will not be in equilibrium. It will just go on like this, right? F equal to ma, we know Newton's law. So there will be an acceleration. So for it to be in equilibrium, the total forces that are applied here should be equal to zero, right? And similarly, we also have total summation of moments is equal to zero. So moment is nothing but it's an external act of, it's a kind of a external load, right? And if there is an external moment on it, the total body will rotate. Let's say we are applying only moment on it, and if there is no equilibrium, it will start rotating like what we see in space rocks and all, right? And even a fan is a good example of it. We are applying a torque on it, and that's why it's rotating continuously, right? Okay, so this is a moment, and as someone rightly pointed out, let's say we will take the same rock and we apply two equal and opposite moments onto it. So what is the net moment on it? The net moment is going to be zero. So that means that this rock is not going to rotate, it's going to stay still. But it will create internal stresses, isn't it? Yeah, so those internal stresses are created, and to study that we need to first cut this rock and see what is happening internally. From externally we can't understand much, because from externally we know that it's in equilibrium. When we cut it, what we see is that if we take only this portion of it, I'll use a different color. So let's say this portion of it, and then see if there is a moment here, then we also know that this rock is in equilibrium. It is not going to rotate, it's going to stay still, right? That means that internally there should be a moment here, right? So this internal moment that we are seeing is what is called as a bending moment. So bending moment is the moment that is created internally to a body so as to resist the loads that are coming from outside. As Gaurav, I think it's Gaurav, right? So he rightly pointed out. And external moments are those loads that are coming outside of the structure. So one is external, one is internal. To summarize it, right? So I think this classifies the difference between a moment and a bending moment, and we can easily compare it with force and axial force or shear force, right? So same situation happens when we talk about forces or axial forces or shear forces. So when we talk about forces, this is a total force onto a structure. So this is a net force on a structure. But if you have two equal and opposite forces, the net force is zero, but there will be a net axial force. So axial force is internal, and when we talk just about force, we talk about the external force, and that is what is coming from external objects. Okay, fine. I think this should be clear. Then we will go on and talk about static indeterminacy now. Now I think someone said that static indeterminacy is the total number of internal these forces, whatever we are talking about, right? Bending moment, axial forces, shear forces. Those are the unknowns because we need to know them, to understand the structure, how much stressed it is, right? So those are the unknowns. and including the support reactions, because without support reactions it's difficult to know the total unknowns, total forces that are acting to the system. By the way, I need to emphasize that even the support reactions are external forces, right? If you have support, these supports are going to give some forces to it, right? So we need to also know what is the total support reactions as well as the internal forces, and these everything put together form the total number of unknowns. And if they are equal to the total number of equilibrium equations, then well and good, we can solve the system just by using equilibrium equations. So we are saying that it can be determined, it can be solved. So a different word for solved is determined, so it becomes static determinacy. Since we are talking about static, means we are talking about forces and moments, loads, right? And that's how this summarizes it. So then what are static indeterminate structures then? You would be knowing it. It's nothing. In a case where you have the total number of unknowns to be greater than the total number of equilibrium equations you have, then you cannot solve just by using equilibrium equations. You need to have additional set of equations, right? And those systems are called as the static indeterminate systems. So can you give an example of a static determinate structure and static indeterminate structure? A cantilever is an example of determinate structure. Okay. By the way, um, again we would ask a conceptual question. Let's say that you are saying cantilever is a determinate structure. What we mean by that? For any given loads, what can we do in the structure? Yes, that's a thing that we need to keep. Can I find out the deflection here? But can I find the deflection only using equilibrium equations? Huh? Actually I didn't hear anything. Can we find the deflection in a cantilever structure subjected to force using only equilibrium equations? Gaurav, your voice is very low to me. I am not sure whose end it is the problem is in. Ah, yeah, it's better now. Still, I'm not audible. Can someone reiterate it? Maybe Meenakshi Sundaram. If you could hear him, can you reiterate it? Okay, method is fine. I'm just asking. Method is fine. The question is, would it involve only equilibrium equations or would it involve something else too? Is equilibrium equation? Yeah, come. Yes, but that's a question. So we talked about, we said that determinate systems, we need only equilibrium equations, right? Then why are we talking about compatibility or constitutive relation here? Is that right? That is what I wanted to know. To think about it, you can actually see what we mean by compatibility and what do we mean by constitutive relation. Constitutive relation means that it depends on the material that we use, right? So for example, we could use a steel here, we could use a paper here, we could use a glass here, we could use a rubber here, right? So do you think that all of these members will have same deflection? Yes. 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 And when we talk about the compatibility, we are talking about the boundary conditions and how it is there, right? So it also depends on that, right? So deflection is not going to depend only on equilibrium. It also depends on constitutive and compatibility equations, right? Then why are we saying that in determinate structures we need only equilibrium equations? Hmm? Yes, so that is something that we need to highlight again and again. So we should not forget it. It's easy to get caught in these things, but the thing that we need to note here is that equilibrium equations are sufficient to calculate the internal forces only. We don't talk about what is the deflection, displacement, or anything else, right? So that those things do require compatibility and constitutive relation. We are talking that if we are interested in finding out only the internal forces, then equilibrium equations are enough in determinate structures. But for this itself, for finding internal forces itself, if we require compatibility and constitutive relation, then it is an indeterminate structure. Okay, and in both these cases, we would require constitutive and compatibility equations if we are interested in finding displacements, deflections. Okay, so that thing is very important to note. So can you give an example of an indeterminate structure? What is it? Yeah, propped cantilever is a very good example of, yeah, fixed and continuous are all examples of, and yeah, yes, good. Okay, so these are the things that we have already studied in structure analysis, I think. Okay. Um, okay, so then if we go and talk about kinematic indeterminacy. So what is the difference between static indeterminacy and kinematic indeterminacy? Maybe should we see a few problems here? If you want, maybe we can discuss a few. For example, can you find out static indeterminacy of some complex shapes? So let's say we have a portal frame, and I hope you know the trusses and all. You would know, right? It's we have a formula, Maxwell's formula. Okay, we'll start with trusses. I think there are some important concepts that we can discuss there. For example, let's say we have a truss. By the way, we talk about determinacy only when the structure is stable. So we already talked about unstable things. Only when it is stable, we talk about determinate or indeterminate. For example, let's say we have a structure something like this. So it's a truss system. All the ends are pinned. Okay. So can someone say whether it's statically determinate, indeterminate, stable, unstable? Determinate. How do we know? Because it's made of triangles. Yeah, that we could get from intuition. But yes, yes. But having triangles is only not enough to know. Yes. So, for example, I can have something like this. Is it stable? Yeah. So it's externally unstable. So we have concepts of external stability and internal stability and so on. But yeah. So how do we know? Because we know Maxwell's rule, right? What is Maxwell's rule? Yeah. So yes, m plus r equal to 2j is indicates static determinacy. By the way, we should say it indicates. It won't prove anything. It will just indicate whether something is statically determinate or not. Right? And how did we come up with that formula? Any idea on how we came up with that? So basically, it comes from the definition of static determinate, right? Static determinate means total knowns is equal to total unknowns. What are total? Yeah, total unknowns. Yes, so total unknown, every bar we don't know the actual force, right? And that gives, if m bars are there, m unknowns will be there. And if reaction suppose also we don't know, yes, that's also unknown. If it is equal to, and how many equilibrium equations you get, every joint would be subjected to many forces. And all these forces we can take equilibrium equations in two directions, horizontal and vertical. Yes, exactly. So two times of joins is the number of total number of knowns. So if this happens, then we say it is determinate. No, we don't say. We could have an indication that it is determinate, right? So why am I emphasizing this point is that we can have a structure where this is satisfied. It it is not statically determinate. So let's take an example. So let's say we have a truss. This is a very common example you would have seen, probably. So let's say we have a structure like this. Okay, this is again a truss system. Can someone find out this m plus r and 2j and say what is the m plus r minus 2j gives rise to? How many members are there here? 1, 2, 3, 4, 5, 6, 8, right? Or 9? Yeah, m equal to 8. Good. And then what are the unknown? R is again 3 only. Yes. So m plus r is going to be 11. And what is 2j? How many joints are there? So, why is it 9? Oh, yeah, there is one more. Yes, yes, yes. Yeah, sorry, I left a member here. You're right. So 9 plus 3 is 12. Okay. Number number of joints is 3, 4, 5, 6, right? Okay, there is no joint here, okay? It's just going behind each other. So joint is equal to 6. Joint is equal to 6. So 2j is going to be 12. So we know that m plus, yes, m plus r equal to 2j is satisfied. That means that Maxwell's rule says that it is probably statically determinate. But is it statically determinate? Unstable. Why is that? Which is deficient, which is redundant. There are both of these things in this. Yes. Yes. So you are right. So actually, if the same structure, I take one of these bars and put it in the other rhombus, yes, diagonals of the other part, then it would become, so let's say I'm taking this portion and putting it here. Then this would become statically determinate, right? So then what is the problem with Maxwell's rule? Why is it giving a wrong indication? What is failing in Maxwell's rule? What is that is missing in Maxwell's rule that is making this mistake? It's not considering what? Yes, stability is a necessary condition, but Maxwell is missing that definitely. But why is it missing that? What is the concept? Yes, we are only thinking about static determinism. That is what we want to find out. And but somehow, what are we not considering when we do this? Uh, Doing this Maxwell's rule. Stability, yes, but why stability is not being considered as a question? Static determinate means that it is stable actually. So yes, so only when we have a structure to be statically stable, then only we can say that it is statically determinate or indeterminate. So if I have to put it as a flow chart, I can say that we have unstable structures and we can have stable structures. Under stable structures only we can have determinate and indeterminate. So once we say that structure is statically determinate, then we definitely mean that it is stable, right? So that is why we should not call this as an determinate structure because it's unstable. First of all, we need to check whether it is stable. Then only we can say whether it is determinate or indeterminate, right? So you are right that it is not considering stability, but I'm trying to understand what did we do wrong that it is not considering stability, or in other words, what should we do so that we can consider stability? Let's say that Maxwell missed it and you want to find out, is it the number of members? Because number of members is good enough. We saw that we can reconfigure this same number of members to make it stable. What is it? Yes, yes. So basically the other synonymous word for configuration is geometry, right? So we are missing the sense of geometry in the structure. We are only counting the number of members and number of unknowns and so on. We are not talking about how these members are distributed. Arranged, exactly. So that is what we would be doing in this course as well. We will be doing a rigorous way of analyzing, and we would be able to find out something is unstable or not using stiffness matrix and so on, right? So here what we need to understand is that Maxwell's rule talks about only the number of members and the number of unknowns. It doesn't talk about how these members are arranged. So it is important to note these angles and so on to know whether it is stable or not. Angle, the position, which member it is connected to, and so on, to know whether something is stable. Why I am saying about angle is, I'll give you an example to understand why angle is important. Let's say that we have a system like this. This is a two-bar truss. Okay, both the ends are pinned so that, okay, and you have this hinge here, and here. It's a truss, right? So is it a stable truss? Is it stable? How do you find it out? Yes. So if you use Maxwell's rule, we will be able to get m is equal to 2 and r is equal to 4. So m plus r will be 6 and 2j will be 1, 2, 3, 3 into 2 is 6. So Maxwell's rule says that it is stable and determinate. We also get a sense that it is stable and determinate. Therefore, we guess that it is a statically determinate structure, right? But what will happen if I take the same truss and make this angle very close to 0? Yes. So will this still be stable? Why not? Yes. So it will actually, what will happen is it will get snapped through. We say that it is snap through buckling. So what happens is that it will go into this configuration. Okay. And where have you seen something like this happening? Very common examples. Can you see where it is very similar to what we are talking about here? Doors. Doors, I'm not sure. Doors, do we have snap through buckling? We just have it as a mechanism, right? It just is a neutral equilibrium. But this is not a neutral. It takes a certain force and suddenly it snaps into different configuration. Maybe if you take a course on stability, you will see all these things being discussed, okay, in detail. But we can understand this. Very good example of this would be, let's say you have even in chairs, what happens is sometimes when you sit on it, it will just tabak, it will go inside, right? It will make a sound and then it will pop out again. When you stand up, it will pop out again. And or you have like some boxes like uh, Bonvita box and all used to come. No, not box. What is it? Bottle. Bonvita bottles and all. There is a cup for it, right? And top cap. And the cap and all, you can see that you can play with it. When you press it, it goes inside, and then when you leave it, it pops out, right? So it's very similar to that because here we are talking about 1D, but if you talk about 2D, you can have surfaces. A dome, very small curvature here, right? So if you press on it, it will just buckle and then it will become like a bowl. And then once you leave it, it will again come to the dome shape, right? So these are the things that will happen. It's happening because of the angle. If the angle was very steep, then it would not happen. Okay, why this is happening? If you want to understand it mathematically, you can find out. If this is P, then actually the internal forces here you can, if you do equilibrium, you will find out that it is P by 2 sine theta. Okay, you can do this. It's simple only. Once you find out this angle P by 2 sine theta, what happens to this P by 2 sine theta as you increase P? This theta is very small, right? So P by 2 sine theta will be huge because theta is 0, close to 0. When theta is close to 0, P by 2 sine theta is shooting up, right? For a given P. And that is why when you plot with respect to theta and how this, let's say this force is internal force is some F maybe, or T is a good symbol, right? T is what we use. So T, if you plot it with respect to theta, you'll observe that it will be it will be a finite when theta is equal to, when theta equal to 0, T will shoot out to infinity. Right? Something maybe this might be a probable graph for this. Right? When theta is close to 0, you have T to be very high. When theta goes to 90 degree, then you have it to be about P. So maybe this might be the graph. This is P, and maybe this is 90 degree. I'm just guessing. Okay, I don't know. But this is what is the graph. When theta goes to 0, T shoots out. Is what is the understanding we have, right? Okay. So that is an example where we need to be careful. Our Maxwell's rule will say that it is stable, but not stable. It doesn't say it's stable. It says that it is statically determinate, and that means that it is stable, but actually it is not. So we need to be careful. It's Maxwell's rule is just an indication. It is not a rule per se, just an indication. Okay. Uh, then what else were we talking about? Yeah, this is about trusses being stable or unstable, right? We have at least a Maxwell's rule. But what about frames and other structures? How do we find out static determinacy? Let's say that we have a beam structure. So let's say we have simply supported. How do we know that this is statically determinate? Is there any rule here? Every one of you knows that, every one of us knows that this is a statically determinate. But how do we know? Yeah, but how do we know the unknown? So what we so instead of having a rule, we are just doing it manually. So we are cutting it, and then we are saying that each part, hey, there is a part like this, there is a part like this, right? And then what we do is that we say that there are going to be, in general, there will be three unknowns, right? We can have shear force, axial force, and bending moment. So we can have axial, shear, axial, and bending. And there are three unknowns going to be generated here. And here already there will be two unknowns, horizontal and vertical, right? And here there will be one unknown, only vertical unknown is there. And there will be three more unknowns here, right? Am I right, or is there something that we are missing here? Can we write there are three unknowns here totally? These three unknowns are already known because these three unknowns will be same as these three unknowns. Okay. So this is same as this. Therefore, we take only one of them. Okay. And that means totally how many unknowns we have? 3 plus 2 is 5. 5 plus 1 is 6. Total unknowns. Okay. And how many knowns are there? How many nodes? Each part of the structure has to be in equilibrium, right? So we can apply three equilibriums in all these two cases. I mean, yes, yes, but you need to be careful here actually. Yeah, so this is something that we need to see properly, because when we know that this roller cannot take any horizontal loads, this thing would become 0, and this thing would become 0, here also it will become 0. Okay, so you can actually do it for complicated examples. For other examples it will be very quite simple to understand this. So equilibrium equations will be 3 and 3. Less stable to more stable, what do we mean by that? Yes, 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 left side you mean, right? Yes, we can proceed from any side. It won't matter, I guess, because in any side what we are going to have is that there are totally three number of equilibrium equations. Okay, yeah. So what we are going to say is that we will, the total number of knowns is 3 here, total number of knowns is 3 here, 3 equilibrium equations and 3 equilibrium equations. That means that total knowns is going to be 6 again, right? So these two tallies, and then we say that it is a statically determinate structure, right? So what about complex examples? We can take a very a complex example and try to understand. Let's say we take a frame. Can someone say what is the static determinacy of this? Don't think that I solved a very simple example and I'm giving you a complex example. We'll solve it together. But I just want some clues to solve this. How do we solve this? How do we know what is the static determinacy of this? Anyone? I don't. We don't need the answer because it's difficult to find out the answer. You can just give a clue of how to proceed. Yes, Meenakshi Sundram. Yes. Yes, but how do we know? Yeah, how do we know how many number of internal unknown forces are there? Yes. 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 Exactly. Yes. 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 So actually, we can cut it into any number of pieces. That's the beauty of structure analysis. Like we don't make a mistake by cutting into different pieces. So we can cut it into anything as much till we are satisfied. Okay. So for example, we can cut a section here. Okay. Okay, and we can cut a section here. Maybe. It is the simplest I could think. You can also cut it here, 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 anywhere you want. Okay, everything will give the same answer. So what do? We split it into different. Now these have become different structures. So the first structure is like this, right? And the second structure is going to be like an inverted F with a. This is what is the second structure, and third structure is going to be like this, right? Now how many unknowns are going to be there? So at this point there will be three unknowns. We'll just write 3, okay? There will be shear force, axial force, and bending moment. Again, 3 unknowns will be there here. Now, I don't need to write this 3 because it's redundant, okay? So, I'll just mark it with black pen. These 3 are same as these 3 due to Newton's third law, right? So, I can have 3 here. And then, there are going to be new 3 unknowns here that have been generated. And those 3 unknowns are known here, right? And apart from this, we also don't know these 2 unknowns. What are the 2? Vertical and horizontal. Here, vertical, horizontal, and moment, right? Here also 3. So how many total unknowns are there? The blue ones, summation of the blue ones. 15, 17, good. So summation is 17, right? And how many known equilibrium equations do we have? 3. Is it 3? No, 3 for the entire structure, right? Now we have cut it into these many pieces. Yes. Yes. So it's 9. 3 into 3 is 9. Okay. Yeah. So summation of knowns is 9. So when we subtract both of these things, we'll get it as 8. 8 What is it? Why do we need 3? Yeah, no, external unknowns are what is counted in these 2, 3, right? External, those are unknowns. Though they don't come into equilibrium equations. Equilibrium equations means in a structure we'll sum everything and then we'll take it as summation of fx equal to 0, right? And these two will be counted in unknowns, these 3 and these 3. Is that clear? So when you sum everything and then when you do when you subtract, you see that there are totally 8 unknowns, right? 8 additional unknowns. That means that it is statically indeterminate to the degree of 8. Okay, this is how you solve any structure. Maybe there is one, we can solve one more a bit complicated sum so that we become more confident on it and then we'll move on. Let's say we have this structure. This is an internal hinge, okay? Can someone find out what is the static indeterminacy of the structure? This is an internal hinge. Internal hinge means that so okay. So what I can do? What is it? You want to know what an internal hinge is? Okay. Yeah, basically it's free to rotate there. There is no constraint to rotate there. So that is what it is. If we want a detailed diagram, you can have something like this. So the connection would be something like this there. Okay, this is a member, this is another member, and you can have another member like this. There's 3D view of it, like with the thickness effect. Okay. They are not being rigidly joined, like it's not grouted. If you know about RC and all, right? This is how the structure is being built. Right? They can freely do rotation there. Actually, I have shown it to be like they can also slide, but they are not allowed to slide. Okay, there's something like a fixed here, so that they don't slide. They can't slide. Okay, so okay. So what is the answer? Some what is it? Three. Someone else have got the same answer. So maybe we'll solve it together. One way, what we can do is we can cut that portion so that it becomes easy to solve, right? Because it's difficult to understand, so we'll cut it that portion itself. So what do we get? We'll get three different structures, right? So the first structure is going to be this. Second structure is going to be this, and third structure is going to be this, right? What are the unknowns that are going to be there? Can someone say how many unknowns will be there here? Two unknowns, right? We don't have any bending moment there, because at the point of internal hinge we know there is no bending moment, so there can be shear force and axial force, only two unknowns, right? But what we will do is that we will not write it as 2, because I'll explain why this happens. Let me say that there is going to be uh, some shear force and some axial force, no bending moment, right? And similarly I can have some shear force and some axial force, and again here also I can have some shear force and some axial force, right? Now what, let me name it as v1 f1 v2 f2 and so on. Okay, this is f2 and this is v2 and this is v3 and f3. Okay, so we might think that there are 2 plus 2 plus 2 6 unknowns there, but we also know from Newton's law that addition of all these forces should sum up to 0, right? Why I'm saying this is, if you would have had only one portal frame and if you're cutting at that point, we say that we have two structures, and each structure we are saying that there are three unknowns, and we are not taking these three unknowns because we know that they are negative of it. So how did we know these are negative of it? Because if this was f1 and that was f2, we know that f1 plus f2 equal to 0, right? That's what we are doing. We are saying that f1 plus f2 equal to 0, so f2 is known. That's why we are not considering this f2 in the previous problems and all. Now since there are three structures, we cannot directly say that f1 equal to minus f2, but we can only say that v1 plus v2 plus v3. Here it will not be v3 from the sign I took, it will be f3. Okay, because all are vertical direction. Okay, if you notice. So there is one condition here. Again, in horizontal condition, you will have f1 plus f2 plus v3 equal to 0. So you have two additional equations. Okay. These two additional equations we also considered earlier. Only thing is that we considered it inbuiltly while not ignoring these three unknowns there. Right now we are including it and then considering these equations. Is that becoming clear, or should I explain in more detail? Okay, so what you can do is that there are six unknowns, and additionally there will be like three more unknowns here and one more unknown here. So 9 plus 1 is 10 unknowns, and equilibrium equations will be 3 plus 3 plus 3 9, and you should also consider these two more unknowns. Okay. So that you have to consider in number of number of known equations. So in addition to 3 plus 3 plus 3, you will also have two additional equations. So there will be 11 knowns. So it seems that it is an unstable structure, right? So 10 minus 11 is 1 minus 1. Does it look like an unstable structure? I am surprised. Maybe it is. Maybe this part will just rotate off, I guess. This one, both it is also a roller, and also, oh, I think we ignored three more unknowns here. I'm sorry. There are three more unknowns here. Yeah, I made a mistake here. So there is 3 plus 1, 10 plus 3 is 13. Okay. So this will be 13 minus 11, which is 2. Okay. So that is how we solve for statically determinate, finding out static determinacy. Right? Any questions here at this point? These are just revision of previous course, so I think it should be followable. And mhm, 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 mhm. Yeah, yeah, you can determine it in any way as long as you're comfortable with it. But I would suggest that not to remember any formulas as such. Yeah, because for example, in these cases, in these examples, it suddenly becomes confusing of where is this 3A or 3C, where is a box kind of thing where there is no closed thing. So how do we do? We get stuck on it. Okay, so it's always comfortable and convenient to understand what we are doing and do it like that. So to do it quickly, yeah, formulas are helpful, but then if there is a way to solve it using the first principles, I have found it useful if we can use first principles. Okay, so it will improve our clarity and confidence rather than trying to memorize a formula without understanding how it came. If you know the details of how it came, that's fine, that's well and good. Okay, yeah, sure, you can use any formulas. Yeah, fine, that is okay. And then we'll move on to kinematic indeterminacy. Maybe we'll stop in a couple of more minutes or 5 minutes more. Before that, I just wanted to close off with kinematic indeterminacy. So, what is kinematic indeterminacy? I think that we have summarized about static indeterminacy, right? We haven't left anything, I guess. Anything important, very much. So, can someone say what is kinematic indeterminacy? Uh, Yeah, good. Then we need to first understand what is degrees of freedom, right? So, first we'll talk about that then. So, what are degrees of freedom? Those are classifications of degrees of freedom, right? Independent coordinates. Uh, okay. Motion. That I think we would have studied in physics, right? So we would have studied that we need two independent coordinates to find out the motion of a body which is translating in a rigid body. Motion we don't talk much in structures, is it not? Yes, I think so. I'm not sure. I think we don't talk much about motion here. We have all the structures to be in equilibrium. So independent is right. Yeah. Yes. 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 So basically, I think whatever Tahsin, right? Tahsin, if I'm pronouncing it right. So he said only it's independent coordinates to define the deformed configuration of a system, right? Or to define the deformation of a system. I think that makes more clear. That makes it more clear. So it's very similar to what he said. So you have, let's say, a truss system. Let's say we take a single bar and we want to know how this bar is located. To know what is its deformed, after deformation it would have moved somewhere else, right? Let's say that after deformation it's looking like this, right? It would have elongated and so on, and it would go like this. Is a part of a system, this is a part of a truss, this is a single bar, and after deformation it would have moved somewhere like this. So if we need to entirely describe this deformation, how many uh, points do we need, how many nodal coordinates do we need to know what is the displacement of these 2 points, right? So in other words, we need to know both the x displacement and y displacement of this point from here. So 2, and again we need to know what these two are. 2, right? Okay, so that means that the degrees of freedom for this bar is how much? 4, right? Total. Now, can someone say, let's this bar be actually rigid? Then what is the degrees of freedom for this bar? What I mean by that is, someone is saying that this bar cannot expand; its length is constant. Then what is the total degree of freedom for the system? Yes, very good. Yes, very good way of seeing it. 3, in a way that what he's saying is we can just find out how this point is moving. Somewhere it has moved from here to here, x displacement, y displacement. After movement, we just need to know we have fixed this point. Okay, maybe we'll fix to the same point. So it has moved from here to here. So there are two uh, degrees of freedom here required. And then we need to know how much angle it is rotating. Because once the angle is known, we know the length, so we can find this point. Okay. So that is a one way to see it. Another way to see is that we have already found that there are 4 degrees of freedom. Now there is one more constraint to it. The constraint is that we know x1 y1 and x2 y2 are the total 4 independent points, right? We need to find out. Now we also have a constraint that x2 minus x1 the whole square plus y2 minus y1 the whole square should be equal to L. Right? That means we have an additional equation. That means the total number of independent of these 4 is only 3. Right? So that is how we have eliminated 1 degree of freedom, and total degree of freedom will become 3 if it were rigid. Okay, good. Then this is about trusses. For trusses, you can just take every point has 2 degrees of freedom for a planar truss. If you have a space truss, you have to take 3. Okay. Now, if you go to beam, every point will have, in addition to 2 translational degrees of freedom, you will also have a rotation, right? So let's say we have a beam element. Now, if I need to entirely know what is the deform profile of this after some loading, it's a part of a frame or part of a, yeah, some structure. I want to know after the loads are being applied, what will be its deform configuration to entirely capture it. How many independent coordinates do I need? This is a planar thing, okay? All these are planar unless otherwise stated. What is it? Should be easy only, right? So translation in these two translations, and then rotation also we have, right? Because the beam can not only expand and do like this, but also can have a rotation, right? So basically we need to know how this, sorry, how this point has moved, and also from this point how much it has rotated. Similarly for this case, how much it has moved and also how much it has rotated, right? So there will be 3 plus 3, 6 degrees of freedom, right? And similarly here again, if you take it to be actually rigid, let's say the length is going to be constant, then how many degrees of freedom? 5, because we are just eliminating one constraint we have, so it is going to be 5. So that's what is about the degrees of freedom. And then we talk about kinematic indeterminacy when we have support conditions. We talk about the total system, right? So for example, let's say that this point is going to be pinned. That means that I'm eliminating 2 of the degrees of freedom. I'm saying that it cannot move. Just like these constraint, what we talk about axial rigidity, we are having one more constraint here. Therefore, if we include that also, we will have minus 2 due to hinge, and this will come down to 3, right? And again, let's say we put a roller here, right? We are arresting one more, so it will have 2 degrees of freedom, right? Due to roller. So it's a simply supported system. So simply supported system will have a kinematic indeterminacy of 2. So what are the two things that we have to find out in a beam that is simply supported? By the way, remember that we have already taken the axial constraint into effect. Okay, if axial constraint is not there, it is 3. So what are the three kinematic indeterminate quantities here? So in a simply supported, we can have a rotation here, we can have another rotation here, and an expansion. The expansion is there, it's not there, then the kinematic indeterminacy is going to be 2. Okay, so we just need to find out the rotation at these 2 points to know the complete profile. By the way, I'll just stop it here with one question. How are we able to say that just by knowing the rotation at these 2 points, we know the complete profile? If we know the rotation at these 2 points, then we know only the rotation at those 2 points, right? We don't know the rotation at this point, and this point, and so on, right? In between points, is it not? I can have rotation to be same. Let's say I'm having the same rotation here at these 2 points, but in between I can do something like this, right? I can have something like this also, no? So just by knowing the rotation at these 2 points, how am I able to say that I have found out the complete profile of this beam? Maybe you can think about this and we can start discussing this problem when we start the next session. Or if you want to say anything now, you can say also. Yeah, it is something related to the beam equation. Yes. Yes, these two things will be the bound. Yes, but I want a more specific answer. Just by knowing this rotation, how do we know whether this answer is right or this answer is right? Or, of course, we know that this is going to be right. Then why is this wrong? Just by knowing this theta, why are we not able to? How are we saying that we know the complete profile? Yes, moment is related to curvature, right? Yes. Yes, but here we are not talking about moment yet. It's all about kinematics, kinematic indeterminacy, right? So we are only talking about if I know the rotation at these 2 points, someone is saying that that is sufficient to find out the whole profile, and that is why the degree of freedom for that system is 2. What it is saying is, if I know two quantities, I know the complete deformation of the it's all about deformation, okay? It's kinematics. So I know the complete deformation of the beam is what someone is saying, and that's what is the definition of kinematic indeterminacy, and that's why we say it's 2. But that raises a question: how are we able to be sure that we know the complete profile just by knowing what happens to the ends? Yeah, what are the assumptions that we make that led to this? Yeah, but that can be satisfied in this profile also. I can have cross sections to be perpendicular to the axis of bending after bending in this section as well, right? I'm not violating here, right? Yeah, maybe we'll think about it and let's start discussing about this from the next class, okay? Okay. One or two questions in the sense like problem wise or conceptually. Can you please be louder? This session that we are right now having. It's always Sunday 3 to 4. It's same timing every week. Yes. They are asking to register to what? Okay. I'm not sure. Maybe I'll get back after inquiring about it. You can also make a official formal question in the discussion forum so that is, yeah, so that I can see to it later and then ask the people before I answer to this. Okay. Yes. What is possible from my side? Yes. Here we will not be discussing on the assignment problems as such, but what we'll do is that we'll discuss the previous year assignments if you want, and then it will be very similar, so you'll get a conceptual understanding on that. And if you have a specific doubt, like you are not knowing the concept to solve the assignment, then you can ask it here so that we can discuss it. Or even if you bring the question here, we'll discuss on what is the way to solve it, but we'll not solve it entirely. We'll just discuss on the concept that is required to solve it, so that you can it will help you to solve it. At this point, I'm assuming that you would know it. That's why I didn't discuss on week 0 assignment, and that was very yes, that's not graded. Yes, yes, that is why I didn't. Yeah, that I didn't bring it here. But from next week onwards, I'll also briefly touch upon previous year assignments, week 1, week 2, and so on, so that it will be helpful for you to solve in the current assignments. The only problem is that last year we did it, and people felt that it's boring. Like we are solving the assignments which most of you would be knowing how to solve. So that is why I started doing these conceptual questions. But if you insist, we can solve on previous year assignments as well. Okay. Okay. If you don't have any other questions, then we can stop the session here. Yeah. Thank you. Thank you. Thank you.